Hello once again, and thank you for joining us on Space Nuts, where we talk about astronomy and space science, and sometimes we talk about space science and astronomy. You just never know with us. Could be all of that. And yeah, good to have your company. Thanks for joining us. And today on the program, we are going to celebrate success on Mars. The Perseverance rover picked up a rock. Woo-hoo-hoo! It's actually very hard to do, but yeah, they've succeeded. And the life of Ingenuity, the other thing that's on Mars, has been extended, which is really good news. We're also going to investigate a new method for investigating the atmospheres of other planets. And I was amused by this story because it involved putting calculations on a piece of paper with a pen rather than using a computer. I was rather impressed by that. And a story about brown dwarf stars, plus audience questions. Peter wants to know about a clock on Pluto. Apparently we put one there. No, we didn't. But if we could, he's got a question about what we might learn from that. We've got a mysterious person from Colorado who didn't tell us their name about dips in light. We'll explain that later. And David in Springfield has a dark matter question about spiral galaxies. So plenty to talk about on the show today. And joining me, as always, is the good Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. How's it going?
I am well. How are you?
Well, fine, thanks, yeah.
Well, yeah, the infection capital of Western New South Wales, I think, is probably a more apt name for our location at the moment. But
yep.
Yeah, we're just plodding along, staying at home, going out once a week to buy food. That's about it. That's about it.
It's much the same here.
Yeah. We're all going through it at the moment. But, the case numbers just keep rising, and we just keep hoping that we reach that magic 70% double vaccination number sooner rather than later so we can get our lives back. But I think we're a bit over a month away from that at this stage anyway.
Yep.
Okay, let's start, Fred. Let's look at our first subject of the day, and that is the Mars Perseverance rover successfully picking up a rock and putting it in a tube.
Well, it's just a little bit more than that, because it drilled a hole in the rock as well.
Yes.
And, of course, this was the issue last time, that drilling holes in rocks doesn't always produce what you want it to. The last time Perseverance attempted to do that, they just got a whole lot of powder that disappeared. So nothing went into the sample tube. But this time they have taken a core sample from a rock, and it is safely hermetically sealed in the container, one of the containers. I think there are 40 of them or thereabouts that the spacecraft carries. One's already been used and is empty because the powder fell out.
Once they have a dud, they can't go back.
No, that's right. I think that's right. You can't just refill that one. No. So the second one is now has its it's got its sample, its core sample, safely in this. It's about the size of an old-fashioned piece of chalk, a little bit thicker than a pencil.
Right.
It's a you commented on that it was more difficult than it sounds, and one of the reasons for that is that actually taking samples on another planet involves a fair bit of technology, and apparently the sampling and caching system on Perseverance is the most complex mechanism ever sent into space. That's the interim director of Jet Propulsion Laboratory. It's got more than 3,000 parts. Our Perseverance team is excited and proud to see the system perform so well on Mars and take the first step of returning samples to Earth. There you go.
Yeah, now, there's the magic words, returning samples to Earth. They're not going to do that for a while.
No, that's right. That needs another mission. So what they do is they put the sample in a container, and then they leave it on the surface, presumably with a flag or a beacon of some sort, so the system knows where it is. I don't think there's any thought of Perseverance going and collecting its samples and then bring them all back to a pile, pile them all up.
So Perseverance takes the sample and leaves it there and then moves on.
Yeah, I think that's the way it works. I think it leaves it and moves on.
Aren't we making this more and more difficult for ourselves?
Well, I guess in the true tradition of good engineering, oh yeah, picking them up and bringing them back—that's somebody else's problem.
Yeah, yeah, we won't worry about that part.
Well,
that's too
don't
hard.
worry about that. Just leave it here, and somebody else will pick that up. Yeah.
Yeah. Good grief.
So,
okay. And the other thing I read that I found interesting was once we do return these samples to Earth, it'll be the first time we've brought back something from another planet. Is that right? I got the feeling we'd already done that.
Not planets. We've done it for the moon, of course.
Yeah.
With Apollo missions. We've done it for asteroids.
Oh, right. That's what I'm thinking of. Yes.
Yeah,
of course.
Ryugu and Bennu and all these Hayabusa missions, things of that sort.
Yeah.
So that's happened, but never a planet. That's right. It's never been a planet.
Yeah.
And really,
wow.
there's only one that you could do it for, and that's Mars.
Yes.
You could do it for Venus if your equipment didn't melt in the process because of the temperature on the surface,
which is
like Mars is. Yes, that's right. Mars is certainly the easiest.
Yeah, we certainly discovered that plastic and Venus don't go well together.
No, that's right. There's quite a few things don't survive too well on Venus.
Very true.
Living organisms for a start.
Mm.
But it's great news, and congratulations to the team. I think that's a milestone that's well worth celebrating. It's what is it now? 8 months, I think, since. It was February since when Perseverance landed. So, yeah, 7 8 months.
And what of Ingenuity? There's news on that as well.
Well, there is too. That Ingenuity has now completed its 12th flight. Remember, it was only going to have 5, I think, was the total that they expected to do, because they really didn't think the little machine would survive all that well.
And we're talking about the helicopter drone, or
I beg your pardon,
the
helicopter, the Martian helicopter. But it's had its 12th flight, and so what has happened is that there has been a formal extension of the mission indefinitely. So Ingenuity itself will now keep going for as long as it survives and as long as it's providing useful data. But it's doing. It's going to do what pretty well what you would expect a drone like that to do, to scout out the interesting rocks and things of that sort that Perseverance can then go and check out, make sure there's no big obstructions in the way, all the stuff that you can do from an aerial mission. Yeah. There's a couple of nice quotes from Josh Ravitch, who's the head of Ingenuity's mechanical engineering team. He says everything's working so well, we're doing better on the surface than we'd expected. But he also points out we've actually been able to hand winds greater than we had expected. I think by Flight 3, we'd actually accomplished all of our engineering goals and got all the information we'd hoped to get. And so there was a mishap on Flight 6 when one of its, there's a glitch in one of the surface cameras that it uses for navigation, but it recovered from that, and the following flights have been fine. So, so what they're planning is to use it to scout the way for Perseverance to go forward to make a safe path for detecting the rocks that need to be measured. And apparently they did that a week or so ago.
Fantastic.
3rd of September.
Yeah. And of course, what we didn't mention was that these samples will ultimately be examined for microbial life or ancient microbial life evidence, which is fantastic. I also read, Fred, that Ingenuity's life on Mars has been extended because they didn't have a choice, because Menulog had put in a bid to take over once the Ingenuity missions had finished. They were, we don't want them involved. But the pizza delivery test went really well, and that's what sort of sparked Menulog's interest. Yeah.
There you go. That will be it.
Yes.
Yeah.
Most exciting. But yeah, more interesting news coming out of Mars, and they're achieving some incredible firsts.
Yeah, absolutely.
Which, and they'll probably continue to do so. Now, Fred, let's move on to our next topic. And I read this article and I started scratching my head because it reminded me of the incredible frustration I had during school when it came to mathematics. But what really tickled my fancy about this, and we were talking about a new method for investigating the atmosphere of other planets, is they worked it out with a pen and a piece of paper.
That's the way to do it. That's the way Neptune was discovered. Yeah. Neptune, the only planet that was discovered with the point of a pen.
Isn't that amazing?
They calculated where it should be, and somebody had a look, and sure enough, that's where it was. So this is something a little bit like that. And let me just explain what we mean by sort of pen and paper mathematics. It's something called analytical methods. The branches of mathematics now are very different from what they were when I studied maths back in the 1960s. God forbid, it was awful. Computers were just coming in, but we weren't really, using them in the way that they use now for modeling, because computers can, build mathematical models of what's happening with observations, for example, and make really accurate predictions that you can replicate reality in a very accurate way with computer modeling. So very powerful in its technology. But the analytical methods, what you do in that is make a formula. And then that's, it becomes very easy. You can almost do it with a calculator rather than needing computer modeling. So it's a different way of doing mathematics, and it's turned up in a news item, which is something that I've always found quite fascinating, and that is the way the light from an object, like a planet going around a star, the way its light changes as the planet goes around the star, if you're looking from a distance. And the classic example of that, and it's not a planet or a star, but the way the moon goes around the Earth, of course, we're all familiar with the phases of the moon. Its shape changes. Yeah. But if you were observing the moon and you couldn't see any detail, you couldn't see the shape of the moon or any of the, the grey areas on it or any of that stuff, all you could see was the brightness of the moon. You can still learn something because you can plot what's called a phase curve. That is to say, as for just thinking of the moon again, as the moon goes around the Earth, because it's illuminated by the sun from different directions, its illumination changes. And if all you could see was its brightness, you plot the brightness against time and you get this phase curve, and of course it will go up and down because as the most of the moon's disk is illuminated, it's bright. As a thin crescent is illuminated, it's quite faint. But the phase curve has locked in it information about the surface itself, the reflectivity of the surface, and the way that would change as it's illuminated in different ways. For example, imagine a powdery surface, which is what the moon's got. If the light that's falling on it is coming in at a low angle, it will behave in a different way from the point of view of how much light it reflects, as if it's being directly illuminated from above. It actually has different characteristics, and you can think of that. If you think about, say, a powdery surface being illuminated from the side, what the powder particles are all going to cast little shadows, which will change the illumination. Oh, I get it. Whereas, say, if it's illuminated from above, the shadows are all hidden by the particles themselves, and so it's brighter. So that sort of information is locked in it. And what has happened? I mean, the theory of this kind of thing goes back actually to the 18th century. It's quite remarkable, and in fact, a man called Johann Heinrich Lambert, and we still talk about Lambertian illumination in the world of illumination science. I get mixed up with this because I sit on lighting committees for the Australian standards, and they're always talking about Lambertian illumination. Anyway, all that notwithstanding, a Swiss astronomer, he's a theoretical astrophysicist. His name is Kevin Heng, the Centre for Space and Habitability at the University of Bern in Switzerland. He and some of his colleagues have published a paper which has a very nice analytical method. It's just the formula basically that solves something called the radiative transfer equation for isotropic scattering. So there's a bit of complexity for this.
Yes, that's where my brain went. Nah, stop reading.
yeah.
It's all too much.
Mine did that too. But anyway, you can look at it in a new mathematical way, and that is what has happened. And so they've kind of tested this. One of the things that has been done, and I think this is Dr. Heng has done this work. Cassini, remember the spacecraft in orbit around Saturn? It didn't just look at Saturn; it also looked at other planets. So it looked back towards the inner part of the solar system to Jupiter, and essentially measured the phase curve of Jupiter. This was quite early in the Cassini mission in the early 2000s. So Jupiter has a phase curve that had never really been analysed in depth. And so the new computation that Dr. Heng has developed, the analytical method, he's analysed the Cassini phase curves and can show that the atmosphere of Jupiter has clouds made up of largish, and these are still less than a millimetre probably, but largish particles which are irregular. They're differently sized. It's really very nice science that you can deduce something about Jupiter from a little telescope on a spacecraft in orbit around Saturn, just by looking at the way the brightness of Jupiter changes. So I was really impressed with that. I think it's a nice piece of science. It's got all kinds of echoes. We've not got many minutes left to talk about this, but let me slide quickly to something that's similar in a way. You may or may not be aware of this, Andrew, but if you look at a rainbow, there are certain features in the rainbow that tell you how uniform the particles, the raindrops are. If you've got, there are things called supernumerary rainbows which appear within the rainbow, and the more of those you've got, the more uniform the droplets are that form the rainbow. And so, just by looking at a rainbow, you can learn something about the droplet size of the cloud of water droplets that's forming it. And this is a kind of analog. So just by looking at the way Jupiter's brightness varies, you can work out something about the particles that are actually in its atmosphere. And it's really neat science.
Yeah, indeed. Yeah. I also read that they're using the same method to analyse the exoplanet Kepler 7b. So this can apply to all sorts of situations by the sound of it.
It's really going to come into its own with exoplanets. That's right.
Yeah.
And what will really make use of it is the James Webb Space Telescope when it looks at the phase curves of exoplanets, because you can do that without actually seeing the planet. You can look at the light of a star and see slight variations in that brightness that come from the phase curve of a planet going around it, even though you can't see the planet as a separate object. Kepler will certainly make use of all that. So I beg your pardon, James Webb Space Telescope will make use of all that. I think we'll learn a lot. And this technique that has been developed, I think, is a really neat piece of work that contributes to that.
Yes, as long as they don't forget when they launch the James Webb Telescope to send a pen and a piece of paper up with it.
That's the trick.
So otherwise it could be in trouble.
Absolutely.
Yes. No, fascinating. And if you want to read that article, I think you'll find it in one of the papers, Nature Astronomy, is it?
Nature Astronomy, yeah. That's where the paper is, which I haven't looked at because I'm too scared to open that. It will just be mathematical gobbledygook of the kind that used to send shivers down my spine back in.
Yes, as soon as I saw mathematics mentioned in the article, my brain froze. But there'd be people who'd be champing at the bit to read it though. So Nature Astronomy is where you'll find the paper. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
Space Nuts.
You've been listening to the Space Nuts podcast.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.